Good afternoon. So in this lesson, I'm going to go over an example that leads to yet another type of boundary condition that involves both the value of the function at the boundary point and that of its partial derivative. So let's review briefly what we just did in the previous lecture. So, for the one-dimensional heat equation, we encounter basically two types of problems. One of them in which you have prescribed boundary conditions, prescribed temperatures at the endpoints. So for instance, you could have a specific temperature on the left endpoint. Let's say you have 1 degree on the left, and then a specific temperature on the right endpoint. Here I have an object of length c. Let's say you have 5 degrees. These type of conditions in which you have values at u, at the dependent variable u, at the boundary conditions, these are called Dirichlet conditions. Lots of parts of PDE theory are named by various mathematicians, including different types of boundary conditions, because that's a big deal. You'll see, you change the boundary condition, that changes completely, maybe not the way you solve the problem, but the way the solution looks like, completely different. So a Dirichlet problem is basically the one in which boundary conditions are values, prescribed values at boundary points. Then there are conditions that came from prescribed flows at endpoints. So remember the Fourier law of heat conduction, denoted by phi of xt, that's proportional to the temperature gradient minus q u partial x of xt. So when you have prescribed values of the flow at endpoints, then you had essentially conditions that dealt with values of the of the temperature gradient of u partial x at the boundary points. You could have, for example, a positive flow on the left side and a negative flow on the right side, let's say -1. When all conditions are in terms of partial derivatives like that, these are called, again by a mathematician, Newman conditions, or a Newman problem. These are the two types of problems we will deal with in the beginning, but the purpose of today's lesson is to discuss an example in which you have mixed conditions, in which conditions come up in terms of both the value of the function and or its derivative. So one application that leads to such a situation is the so-called Newton law of cooling, which might as well could have been named Newton law of cooling or warming, because it works in both directions. This is the situation in which the environment surrounding the object has a constant temperature. Because normally all objects, including the environment itself, are in constant thermal exchange, right? I mean, there is a thermal exchange of energy, heat energy, between the objects that come into contact until eventually they reach a thermal equilibrium if the process goes on indefinitely. So that means technically the environment itself is influenced by the object that is in it. If I bring, for example, a very hot object inside a room, a cold room, the object will cool down because the room is cold, but the room also will warm up a little bit because of the object. However, if the difference between the two in size is so huge that the environment for all practical purposes doesn't really change because of the object, then the exchange goes into one direction. So the environment affects the object, but not the other way around. If I bring a small ice cube in a hot room, the room will melt the ice cube, but the ice cube will have a negligible effect in the temperature of the room. You can't say basically that the room gets colder because of the ice cube. So in a more formal way, the Newton law of cooling states that the flow, so let's pay attention actually to the terminology here, because we're going to have to put this into math. math. So the flow of heat, the flow of heat energy across the surface of an object is proportional to the difference between the temperature of the surface temperature and the environment temperature. All right, so basically what it states in math notation, for at least for the one dimensional heat equation, it states that the flow at a point on the surface x and at time t is proportional, so we're going to have a constant of proportionality, times the difference between the temperature of the environment, let's call it T, right? So let's call big T the temperature of the environment, and that of the surface of the object. So X is a point on the surface, keep that in mind. And it's not clear in which direction is this difference. Is it T minus U or U minus T? It only says the proportional to the difference, but it all depends on the convention on how you want to make the flow positive, to the left or to the right. So it could be in both ways. You'll have to basically look carefully and decide which one is which. We will do that in a minute. It's not a big deal. Just have to make sure that the sign is correct according to our convention, that the flow of heat is from left to right and the negative flow is from right to left. So this phi of x t should be either positive or negative depending on whether the flow is to the right or to the left. This big H, like with all formulas like this, is a physical constant. This is basically the surface conduction term. It's the ability of surface material of the object to conduct thermal energy or heat. All right, so how do I actually write down conditions like this for the object under our convention? Because the heat equation we derived on the top of the page, remember, is under the assumption that the object is insulated on its length and the heat flow can only come to the left or to the right of the object. So you have basically an environment of temperature T1, let's say on the left, and an environment of temperature T2 on the right. So T1, temperature of the environment to the left, and T2 will be the temperature of the environment to the right of the object. This is because of the geometry and the simplifying assumptions we made in this problem, right? So insulation along its length, the actual environment is whatever comes into contact with the left side of the object and whatever comes into contact with the right side of the object. So there are two instances of the Newton law of cooling. Now you have to be careful because the Newton law of cooling states what happens on the surface of the object. So it's not for any x. If I want to write the law of cooling for the left side, I'm going to restate this law, but for x equals 0, because that identifies the left endpoint or the left side of the object. And let's see which one is which. Is it t minus u or u minus t? So phi of 0t is the conduction term h, and if you look carefully, it's gotta be t1 minus u of 0t, not u of 0t minus t1. Because if the temperature T1 is bigger, so imagine for instance you have for the object here, imagine T1 here is hot, and then right here on the surface you have a cold point. Then the flow should be from left to right, should be positive flow. So the difference should be T minus U, not U minus T1, right? So if T1 is bigger than U of 0T, the temperature on the surface, then the flow should be from left to right, therefore it should be positive. So T1 minus U, big minus small, that's a positive quantity, so therefore you don't want U minus T1. For exactly the same reason, the opposite is true for the right endpoint. So the flow at the right endpoint, or the right edge of the object, is going to be H times U of CT minus T2. Once again, imagine here that right here at the edge of the object, when x equals C, imagine you have a hot surface there, and let's say the temperature of the environment, T2, happens to be cold. Then again, the flow should be from left to right, and therefore it should be U minus T2, not T2 minus U, right? So that we have positive flow. Of course, if the difference is the other way around, you know, let's say cold and hot, then of course the flow is reversed and it should be negative. So the reason is T1 minus U on the left and U minus T2 on the right is simply because of the geometry of the way we set up this object and the way we convene. We made the convention that flow is positive from left to right. All right, what does that mean in terms of the boundary conditions? Because remember, when you establish the flow conditions, everything should be rewritten in terms of the conditions on U of xt. So this is the time when you have to replace the flow with the Fourier law of heat conduction. Look up to the right corner. Big K is the conduction term, so we have phi of 0t because of the Fourier law of heat conduction, that's minus k, big K, right? U partial x of 0t, and because of the Newton law of cooling, that's also equal to h T1 minus U of 0t. And the other point, phi of Ct, so that's going to be minus k U partial x of Ct, which again, because of the Newton law of cooling, that's U of Ct minus T2. And so if you look carefully now, you will notice that the conditions basically are in terms of both U and partial x, right? So for example, you can bring these two into one place. The way you write it usually is to actually bring U to the left side or to combine the constants. So for example, I can divide by minus k, so you have ux at 0t minus h over k t1 minus u of 0t, and then ux of ct minus h over k u of ct minus t2. And in many problems this is also renamed as a different constant, I'll show you actually with an example how this can be renamed. I'm going to show you an example with actual temperatures, but you will see, for example, this big H over K renamed a different constant when the boundary conditions are specified, because in many problems you are not told maybe that this comes from the Newton law of cooling, but you are already given the boundary conditions that involve both the value of the function and its derivative. So what's important for now is that the boundary conditions involve both the value of the function at the boundary point and its derivative at the boundary point. So let's stay tuned for a second page when we go over an example involving this type of condition. So we're going to do basically a steady state temperature involving conditions of mixed type like these ones. So stay tuned. Okay, so I wrote again the conditions, and let's actually work with actual numbers for the temperature. So suppose, for example, the left endpoint has temperature 0 and the right side of the object, the environment on the right side, is temperature 5. And like I said, let's solve the steady state temperature. So we assume that eventually the temperature stabilizes, which means the PDE simply becomes u partial x twice equals 0, which if we integrate it twice, remember this leads to u of x equals mx plus n. So basically we can drop the t, right? If eventually the temperature doesn't change anymore with respect to the time, that means in the steady state, the temperature depends on x only as t goes to infinity. So we can rewrite all of these boundary conditions now in terms of just u and u partial x at 0 and c. So we can drop the t, the little t, and then we're going to find the constants of integration m and n, right? So remember that mx plus n comes from integrating u partial x twice equals 0 twice. So with these values, then the first condition becomes minus q u partial x at 0 equals t1 is 0, so that's going to be h0 minus u of 0. And then the second condition, minus q u partial x of c, h times u of c minus t2, which I said is equal to 5. And like I said, it's customary to rename these physical constants. So let's continue rewriting this. If I have minus q u partial x of 0 equals minus h u of 0, and then minus k u partial x of c equals, let's pull the minus out so that I have the same signs. So minus h5 minus u of c, and we divide both sides by minus k. So this becomes big H over k u of 0, and then ux of c equals big H of k over k times 5 minus u of c. There's a similar homework problem to this one, and you should go over this carefully before you go over the homework problem. But this is where I think in the homework you're going to have this constant little h, so you can rename big H over k little h, just to make basically the whole process more manageable when you write down the conditions. U of x0 equals h u of 0, and then little h, right? So ux of c little h times 5 minus u of c. And again, because of the algebra and the way you rewrite these terms, you can see various versions of these types of conditions. Sometimes all of them are on one side of the equality, and then you have some constant to the right. But all of them will involve u and u partial x if it comes from the Newton law of cooling. So now it's time to find big M and n. So obviously u partial x of little x is just m. U of x is again mx plus n. So look carefully now. We apply these, we plug in these functions into the boundary conditions. Partial x of 0, that's just m, because u partial x is a constant, m. And on the right hand side, it's little h times u of 0, which is m times 0 plus n. Second boundary condition is u partial x of c, which is again m. And on the right hand side, we have little h times 5 minus u of c, which is quantity mc plus n. Right, so u of c is mc plus n. You subtract that, Make sure you put the parentheses so that you don't mess up the signs. So the goal is to find big M and N. So M is H times N, and here M is H times 5 minus MC minus N. So let's see what's the easiest way to go about. I think I mean, we can just substitute, I suppose, at this point. Yeah, let's just substitute M with HN into the second equation, and let's expand this. 5H minus CHM minus NH. So I'm going to replace M with HN. M is H big N minus NH. Let's move everything in terms of N on the left hand side. So we have NH plus another NH plus CH squared N equals 5H. And if I pull out N, I get 2H plus CH squared equals 5H. And that gives me, and I can actually simplify by H. So if I pull H over here, I can cross out one H. So I get N equals 5 over 2 plus CH. And from the substitution, we get that M equals little h times N. So that makes it 5H over 2 plus CH. So the steady state temperature U of x will be mx plus n, 5H over 2 plus CH, little x plus n. Or we can factor out 5 over 2 plus CH, and then in parentheses you're left with HX plus 1. All right, so this is basically the solution for the steady state temperature. So make sure you go over this example because remember that many of the problems given in the homework will give you the answer, and you may not know where it comes from, but you have to be patient to do the computation and all the algebra. You may wonder or you may be annoyed why the problem still keeps unspecified values like CH and so on. And the reason is because often, as a matter of practice, you can interpret the solution better if you still leave some of these parameters unspecified. So for example, you could ask yourself, what happens if the object is longer? So what happens if C goes to infinity, for example, or, bigger value? So you look at the temperature and you can see how that affects the overall temperature at that object, right, or a given point. So you can make this type of interpretation, or you can ask yourself, what's the influence of the conduction term, that little h? So there's some usefulness of keeping some of these parameters unspecified. So with that, I think that's it for today. We're going to continue next lecture, we're going to do another steady state temperature, this time in spherical coordinates or cylindrical coordinates, to see how that looks like before we move on with another topic. The next big topic will be the wave equation. Again, an introduction of the concept, and then after that we will deal finally with the main problem of solving a boundary value problem via separation of variables. But that comes a little bit later. So that's it for today.